Let's continue our discussion of triple integrals in Cartesian coordinates by looking at a couple more problems here. Okay, I'm calling this example 3 then from the other two we did before in the previous video. Write the appropriate limits of integration for the triple integral over the solid D f of x, y, z dv. Okay, now I'm taking part of this from problem number 14 in your book. D is bounded by the plane z equals 2y, shown here in the purplish color here, and by y equals 4 minus x squared. Now, if you look at y equals 4 minus x squared, in the xy plane, that would be what? A frowning parabola, right? Okay. Since z is missing here, remember, and we're talking about all points x, y, z in Cartesian coordinates, this would be what? Extruded, this parabola would be extruded in the z direction, okay? So that's where we're getting this parabolic cylinder is actually what it would be. Okay, so where those intersect here, and this is going to be bounded by what here the xy plane also. This is, that's a z right there. Anyways, now they ask you to evaluate the triple integral from the book. I'm not going to evaluate this, and I can't because I'm going to be using as the integrand just some fantasy function f of x, y, z. I have no idea what that is. So we can't get an actual number out of this. In the book, they actually want you to find the volume, I think, so that becomes the unit function there. Okay? Let's talk about setting up the limits of integration, though. Okay? They want dz, dy, dx. Okay, so we shall accommodate here. So I'll write I as our integral. Okay, so that's the triple integral. Fubini will allow us to do what? Write it as an iterated integral. Okay, hopefully just one of them. And I think you can see this is what, a z simple solid here. So definitely we're just going to need one integral here. Put in your integrand. And then they want this order dz, dy, that's dy, and then dx. Okay. Well, now if you take a look at this, where is z going from and to? Okay. Well, if I project the solid into the xy plane, I get what, this parabola in the first and second quadrants of the xy plane. So above the x-axis here, just that particular region here. Z would be going from what? The xy plane is 0 up to the purple plane there to y. Okay. Alrighty, so if I take any point in that region, I'd be going from z equals 0 up to z equals 2y, so good. All right, now, that region which I just described as part of the, the interior of that parabola there in the xy plane, okay? Let's integrate in the y direction first, so y would be going from what? The x-axis, which is y equals 0, out to what? Y equals 4 minus x squared, okay? Now, where is x going from and to here? Now, you want to go in the positive direction, so increasing values of x here. It looks like x is going from -2 to 2. And this would be the final answer for our problem here. Now, for some particular f of x, y, z, maybe we could go back and evaluate that depending on how difficult that integration would end up being. But that would be the general form we would be looking at, right? Okay. Okay, let's do another example here. I'm calling this example 4, but it's essentially the problem number 15 from your book. Okay, write the appropriate limits of integration for the triple integral over the solid D of f of x, y, z dv. Let's describe the solid D. D is this solid bounded by the coordinate planes and by y equals 1 minus x squared and y equals 1 minus z squared. Okay? Do not evaluate any triple integral, and we won't be able to because I'm sticking f of x, y, z in there, just a generic function. Okay? Which order is easier to evaluate? dz, dy, dx, or dy, dz, dx? Explain why. Okay? All right. I'm going to actually show you the easier way to do it here first. Okay? if you take a look at this, the way this is drawn here, and remember, I mean, if you look at this, you can see how important it is to get an idea of the solid that you're actually looking at, right? Okay, it's vital information here to get a visual on this. Now, when we look at y equals 1 minus x squared, we notice that z is missing. Now, y equals 1 minus x squared, we know that's a chunk of a what? A parabola, and that would be extruded in the z direction. Okay, so that would be going straight up like that, as you can see here, the blue side there. Okay, how about y equals 1 minus z squared? Well, that's going to be what? A parabola also, if you imagine in the yz plane. Well, x is missing, so that would be extruded in the x direction. So we get this orangey looking parabola here, parabolic surface, I should say, here. And then they intersect here. Okay, but you can see, I think, that this is what? This is actually a z simple solid. Okay, so here's what I'm going to do first for our integral. I'm going to go like this. Let's integrate in the z direction first. Let's see how difficult this is. Okay. And we'll see if there's any challenges doing it the other direction they suggest. So I'm going to go in the z direction first. If you look at this whole thing, if I was to look at it from the top here, the top parabolic cylinder, and project this into the xy plane, I would simply get what? This blue region here, bounded by these points in the origin, in the xy plane, right? Okay? So we'd have the x-axis, the y-axis, and that parabola in the xy plane being forming the bounding region in the xy plane. Where's z going from and to? It'd be going from what? The xy plane, so z is 0, up to what? Y equals 1 minus z squared. We'd have to solve for z in terms of y, wouldn't we? If you do that, you can actually see that z would be what? The square root of 1 minus y. And we want a positive sign on that square root, right? Because you can see z, well, this is part of the first octave. Okay, so z is positive. Okay, now let's see. Then they said what? Dy dx. Okay, let's see how that looks. Now, I'm going to be integrating over that region that I just mentioned here, bounded by the x-axis, the y-axis, and the parabola y equals 1 minus x squared. If I'm going to integrate in the y direction first, y would be going from the x-axis, which is 0, out to the actual parabola 1 minus x squared, y equals 1 minus x squared. If I project that region onto the x-axis, I would be going from 0 to 1. Let's go ahead and give that a name. I will call it I. So that would be the integral if we use the order dz, dy, dx. Okay? Now, let's go ahead and look at the other way they're asking us to consider. What about dy, dz, dx? Let's integrate in the y direction first and see what kind of problem we run into. Okay? Well, let's go ahead and do it here. So I've got my integral, okay, so I'm still doing this, right? Okay. I is also, let's see. It's going to be a triple integral. It's going to be f of x, y, z. And then they said dy, dz, dx. Okay. All right, so I'm going to be integrating in the y direction first. Now, if you look at it, you guys see, if I project this thing into the xz plane, this is z here, by the way, that didn't come out quite so well. The xz plane here, I actually get a square region. Okay, I get a square region if I project all the points on the solid into the xz plane. I get a square region. Anyway, but is it going to be y simple? And the answer is no. Okay, now I'm actually going to draw the projection into the xz plane of what would happen here. You would actually see this this little curve here where these two parabolic cylinders intersect here. Okay, if I project that into the xz plane, I'm going to put a dashed line in there. I claim I get a straight line. Okay, I claim I get a straight line, and that straight line is very simple. It's going to be z equals x, or x equals z. So I'll just go z equals x, that line. Okay, now how could I tell that? Well, let's go ahead. What would happen if I actually intersected these two parabolic cylinders? I've got y equals 1 minus z squared, but I've also got y equals 1 minus x squared. Now, equating these two, you can see that x squared and x squared and z squared would have to be equal. Okay, that means that would be, well, x is plus or minus z. I actually claim it's plus because what? They're both in the first octant, right? Okay, so as far as the xz planes, we would consider those in the first quadrant there. X and z both being positive, we must have this. And there's my statement there that the projection of that curve of intersection into the xz plane is actually the line z equals x or x equals z. Okay? All right. Now, let's go ahead. Oh, well, I should say, so we're integrating over what? A region 1 and a region 2 of the xz plane. Both those are in the xz planes. Those are two triangles, right? Now, we looked at a problem like that earlier, so this is going to be similar to that. Okay? But basically, I'm going to be integrating over R1. Let's see. Let's say I'm integrating over R1. Where is y going from and to? Y is going from the xz plane, y is 0 in other words, out to what? This parabolic cylinder, which is y equals 1 minus x squared. So that's 1 minus x squared. Okay, so I would have integrated out the y, and I would get in general a function of x and z here, and then integrating out the z and x, I should end up with the numerical value. Okay, let's see. Now for R1, we want to go in the z direction first, they ask us, okay? So we'd be going from what? The z direction. So z would go from the x-axis, which is 0, out to x, right? We want that in terms of x there. And then if I project that onto the x-axis, I'd be going from 0 to 1, okay? Now, that's only integrating over what? R1. I've got to do the same thing. I've got to go over R2 here, okay? And you can see here what's going to happen probably. Let me get this in here. When I'm integrating over R2 here, y would be going from 0 out to what? The orange-looking parabolic cylinder. So y would be going from 0 out to 1 minus z squared. Okay? And once again, when I integrate out y, you see how I get a function of what? X and z here, and then I integrate out z, then x, another numerical value. Let's try another one here. Let's see, where are we going here? I'm integrating over R2, right? Now I want the z direction first, okay? So I'd be going from what? X out to 1, okay? And if I project R2 into onto the x-axis, that would still be going from 0 to 1, okay? Okay, so I would have to actually, in the second case, I would have to do what? I'd have to break it up into two separate integrals. Which order is easier to evaluate? The first one, definitely. The second one, I had to break it up into two separate integrals, okay? Now, I say that with a small proviso here that under certain situations, maybe it would actually be more advantageous to do it the second way, depending upon the nature of the integrand itself. So always keep that in mind as well. Okay, well, that should do you for now.